Okay, so now we're going to talk about the Bohr model. This is a picture of a neon light. And neon lights actually contain neon. The orange here is a glass tube containing neon. And you put electricity through the neon, and it will give off this very distinctive orange color. It absorbs electrical energy and re-emits that energy as light. You can do this with other elements as well. They just don't give off as much light. Here's a mercury lamp. Mercury will give off a blue light, and hydrogen lamp gives off sort of a pink light. And what color you get depends on the element that's in there. So the light that's emitted, here's our hydrogen lamp. If we take the light from that lamp, not from the light bulb that we had before, but from this lamp, and pass that through a slit and through a prism, what we see is not a beautiful rainbow. We only see 3 very small bands of color. There's a red and sort of a blue and a violet. Well, actually, there's a 4th one down there, but that one's even harder to see. So we see discrete lines. So this is also an emission spectrum, but unlike the one from the incandescent light bulb that was a beautiful rainbow, this one just has particular lines of color. Each of these colors is a specific wavelength of light, a specific energy of light. And this pattern is characteristic of hydrogen. Doesn't matter where the hydrogen came from, put it in a lamp and send it through the prism, and you're going to get the same spectrum every time. It's kind of like a fingerprint. So this is the spectrum we see from white light. This is hydrogen. Excuse me. Helium is going to give you some more lines, and notice they're not in the exact same places. And here's neon. Neon gives a lot of lines. And there's a lot here in this orange and yellow, and those are very bright. So these are emission spectra. And what we see is there are discrete lines, not a continuous spectrum. So why? Scientists, looked at those spectra and, of course, asked the question, why? How does that happen? Well, Niels Bohr, one of the guys who eventually worked on quantum mechanics, developed a very simple model to explain this. So this is an illustration of his model. Here we have the nucleus, and in the nucleus you have all the protons and the neutrons. And then we've got the electrons outside the nucleus, and the big question is, what are the electrons doing? So he said, well, I think maybe the electrons are in orbits, and so here's an orbit. We'll call that 1 and 2 and 3 and 4 and 5. These are different orbits. It's a lot like the solar system, where you have the planets orbiting around the sun. So here we have electrons orbiting around the nucleus. And the idea here is that an electron, say, in this second orbit, when you zap it with electricity, can absorb some of that energy and jump up to a higher energy orbit. And then when it comes back down, the energy that's released is given off as light. So the distance between the nucleus and this orbit, this n equals 1 orbit, the distance between n equals 2 and the nucleus, those are fixed distances. They can't just waver around. You're in one orbit or you're in the next orbit. And we call something like that quantized. So the distance from the nucleus to the orbit is quantized. That means also that the energy of the orbit is quantized. And so we specify those orbits by quantum numbers 1, 2, 3, etc. You can't be in between orbits in the Bohr model. And here I've got a ladder. There are a lot of things in real life that are also quantized. A ladder is quantized. You can stand on the first rung. You can stand on the second rung. You can't stand in between, right? There's the second rung, the third rung. You can't go in between. You can't stand there. You can stand on the third, the fourth, the fifth, etc. Our monetary system is quantized. You think about our paper money. There's a $1 bill, the lesser known $2 bill, 5, 10, 20, 50, 100. There's no $75 bill. And our coins are quantized as well. There's no 13-cent coin. There's a 10-cent coin and a 25-cent coin. There's nothing in between. That's something that's quantized. So if an electron in this first orbit absorbs energy from electricity, it can jump to a higher orbit, a higher energy orbit. And it'll hang around up there for a while, but that's not going to be stable, and so it'll eventually relax to a lower orbit. It may go to the next lowest orbit, it may jump down to where it was originally, but when it relaxes, it releases energy in the form of light. The energy here that's released can be measured because we can measure the energy of that light. And the energy of that light corresponds to the difference in energy between those two orbits. This amount of energy that's released is a photon or a quantum of light, a packet of light. Any questions? So this model explained the discrete spectrum of hydrogen. So we see a red line on the spectrum. It's got a wavelength of 657 nanometers, and that corresponds to an electron moving from the third orbit to the second orbit. This blue-green line at 486 corresponds to an electron going from the fourth orbit to the second orbit. And this violet one, 434 nanometers, is from the fifth orbit to the second orbit. The reason that we only see discrete particular wavelengths is because there are only particular transitions that are possible. It's like with the ladder. You can go from rung 2 to rung 1, you can go up, but you can't do stuff that's in between. And so there's no transition here that's between 657 nanometers and 486 nanometers. Does that make sense? So each of the lines that we see on one of these element spectra corresponds to a particular transition of an electron within the atom. So the Bohr model was a great success for hydrogen. They were able to calculate all sorts of things about the different orbits in the hydrogen atom. It's awesome. So then let's try it on helium. Helium has 2 electrons. Doesn't work. The Bohr model only works for hydrogen. So they had to, figure out something else, because the Bohr model working for hydrogen was a big advancement, but it's obviously not the ultimate answer because it only works for hydrogen. So why do we even talk about the Bohr model? We talk about the Bohr model because it's a lot easier to get your mind around than the quantum mechanical model.